Hey, welcome back. In this video, we're going to learn all about computing double integrals. Hopefully by now you're familiar with what a double integral is, and you've been thinking about it using this like slice, approximate, sum, limit process. So today we're going to get into the mechanics of taking a function and taking a region in the plane and actually computing the integral of the function over that region. All right, let's hop into it. All right, so I want to start by motivating what we're going to be doing with what's going to seem like a weird question, which is, okay, here are 12 numbers, and I want to compute the sum of all 12 of them. Okay, so there's no like trick here or anything like that. We could just add up these numbers in order, going 1, 4, 3, 2, 2, 1, and so on, just adding them all together, using a calculator or just keeping track of a running total in our head. But to model what we're going to be doing with double integrals, I want to show sort of a different way to think about how we could add all these numbers together. One thing we could do to kind of like save us from having to keep that running total in our head is first like add up all of these numbers together. So add up the first row, and we get 1 plus 4 plus 3 plus 2 is 10. And do the same thing for the next two. So compute like row sums. So the sum of the second row looks like it is 7, and the third row is 9. So maybe we'd call these row sums. And then to get the total, we'll just add down this. So now we just need to do 10 plus 7. 17 plus 9 is 26. All right, so that's cool. We could have also done it sort of the kind of opposite way, which is add up all of the columns first. So add up this first column, 1 plus 2 plus 2 is 5, and the same for the rest of them. So we could call these column sums. Once we do all the column sums, we have a single row of column sums. So then we could add all those together, and you better believe that we would also get 26 in that case too. Okay, so what was the point? Well, we had this grid of numbers, these white numbers that we started with. This is sort of what we're left with when we're doing a double integral. Remember in the last video, we like cut up Massachusetts into like all these little pieces. And then on each piece, we did an approximation of volume of snow. You can think of these numbers as being like on each grid piece, the approximate computation that we get. So this would be, 1 would be whatever the value of the function is on that piece times the area. That would be 1. And then on this piece, it would be 4, 3, and 2. Remember, the next step of the double integral process was to add all of those together. And in the previous video, I sort of just like hand waved my way through it, and I was like, okay, well, we just add them somehow. It doesn't really matter. Now I want to think a little bit more carefully about how we're adding them, because it's going to inform how we actually like go about computing a double integral. And so what I'm trying to show you here is that we can do that in sort of two ways. We can add across all of the rows to get row sums, or we could have done it the other way, where we do a bunch of vertical sums first to get a row of numbers, and then we do a horizontal sum to get the total. And of course, we got the same thing either way, because it was just sort of two different ways to add all these numbers together. So that's sort of where we're headed with this. When we're talking about integrals, instead of doing a sum across each row and then down the column, we'll be doing integrals. In short, the way we'll evaluate double integrals is as a sequence of two integrals, one that we can think of as like integrating horizontally and then vertically, or the other way around. We can integrate vertically first and then horizontally. Okay, so let's see how that works with a actual example with a function that we have a formula for and a region that is not too complicated. Here we go. So another way to write our goal with this problem is to compute the double integral over a rectangle. I'm going to call it R of the function 6x squared y dA. So that's the notation for the double integral of this function f of xy equals 6x squared y over this rectangle R. We're going to start finding in our course that whenever we're given a description of something and we're not given a picture of it, we should draw the picture ourselves. It says x goes from 1 to 4, so here's 1 and here's 4, and y goes from 0 to 2. So it's sort of like this. So it's this rectangle. Okay, it's actually this filled in rectangle, but I'm going to be drawing stuff in here, so I don't want to like shade this in with blue. But remember, R is a two-dimensional region, so it is like this. It's this filled in rectangle. So going back to our slice, approximate, sum, limit process to compute this, what we're really doing is we're taking this rectangle and slicing it vertically and slicing it horizontally to get like a little grid of tiny little pieces. By the way, we'll call this horizontal spacing delta x, the vertical spacing is delta y. And so on each of these little pieces, we'll take the area of the piece. We always take the area of the piece and we multiply it by the value of the function evaluated somewhere on that piece. So what we'd have after slicing, approximating, and summing is this two-dimensional Riemann sum, right? We ended up with something like this. Remember the sum was annotated with something like, we have one of these terms for each piece. What I want to do is kind of like take that idea from the first thing where we kind of added up all those numbers in that grid and apply it to like sort of rewrite this sum. Because here's what we could do. Instead of saying we're adding up one term like this for each piece in this grid, we could sort of do what we did before, which is add up all of the rows individually. If we're adding up just across each row, maybe I'd write that like this. We're still adding up this f of xy, delta x, delta y, but we're only gonna use one sum because we're sort of doing just like a one-dimensional sum. And we'll annotate this by saying like add across each row. Now, the important thing is that if we're moving horizontally here in this picture, if we're adding across each row, then inside this sum, x is changing because we're moving horizontally, but y is not. So if y is fixed and x is the only thing that's changing, we can sort of cut out this chunk here and say this sum, ignoring the delta y, this, right, in this thing, y is fixed and only x is changing. And what that means is that this is approximately a one-dimensional Riemann sum. And now it's like once we've added across each row, the row sums, which I sort of wrote in the margin here, like we had a bunch of numbers, one for each row in that grid example. For each of these, we want to add them all up sort of vertically, right? All of these different things have different y values. All the different rows have different y values. So we're summing across each row first, and then we're adding up all of the row sums. Okay, we can kind of think about what happens after we take a limit as delta x and delta y both go to 0. What we'll end up with is the stuff inside this blue parentheses is going to turn into a one-dimensional integral where the variable that we're integrating with respect to is x. And since we're adding across each row, x is going to go from 1 to 4 because that was the bounds on x in this picture. The function we're integrating is still f of xy, so it's still that 6x squared y, and we're integrating dx. Dx means, you can think about it like it's like a small piece of the x-axis, or it just means integrate with respect to x. So it's like this inside here, we're integrating across each horizontal row or each horizontal slice sort of. And then on the outside, we want to integrate vertically. So we want to integrate with respect to y. Remember, y goes from 0 to 2, and then we'll put the dy on the outside. So this expression here is how we actually evaluate a double integral like this. For what it's worth, this is called an iterated integral, and I'll show you how to evaluate it in a second, but it is really just doing two one-dimensional integrals in a row. Also, the bounds on x and y actually turns out to be the toughest part of this when you're going to be practicing solving problems, is usually setting up the bounds. That always comes from the region that you're integrating over. So here, x varied between 1 and 4, and y was between 0 and 2. That's why we have these bounds here. We'll talk in a second about what to do when the region you're integrating over isn't a nice rectangle like this. It turns out it's a little bit more complicated, but we'll get there. For now, what I want to do is I want to take this and show you how we actually go about like computing it, like how we're going to actually compute this integral. Okay, so I just copied this from what I had before. I put in the formula for the function that we're actually integrating here because now we're actually going to want to use this. So it's time for us to do a little bit of antiderivative finding. But really, if you are comfortable with computing integrals in single variable calculus, then when it gets down to evaluating these iterated integrals, you're just doing that twice. So the rule is that we integrate from the inside out. So there's an inside integral and an outside integral. We're going to do the inside one first. So what that means is let's just look inside these blue parentheses. We're going to integrate this expression with respect to x. Now, this is sort of like taking a partial derivative. We're sort of taking a partial antiderivative if we're thinking about how to evaluate this definite integral inside the blue parentheses. So what we need to do is think of a function whose derivative with respect to x is 6x squared y. And I said derivative, but really what I should have said is partial derivative. We want a function whose partial derivative with respect to x is 6x squared y. And you can kind of guess, like play guess and check. You'll get a better sense for how this works. But really, you're just treating y as a constant here. So a function whose derivative with respect to x is this would be something like 2x cubed y, right? Because if I differentiate with respect to x, treating y as a constant, this 3 pops down and makes a 6 with this 2, and then the exponent here would become a 2. Cool. So we're evaluating this, use this little bar to indicate evaluating, from 1 to 4. From now on, I'm always going to write x equals 1 to 4, because if you just wrote 1 to 4, it's not obvious whether you're plugging in 1 and 4 for x or for y. But anyways, that's what one step of this would look like. Inside the blue parentheses, that's what changed. The stuff on the outside comes along for the ride, and it's there. We'll get to it later. Next, we still have this integral from 0 to 2. And inside these blue parentheses, we plug in the 4 for x and we plug in the 1 for x. And we get, let's see, 4 cubed is 64 times 2 is 128. So we have 128y. And then we plug in 1 for x and we get 2y. And we subtract them. I'll note that the thing that we used to do this, right, going from this step essentially to this step, that was the fundamental theorem of calculus. That was the single variable. Well, there's only one. There's only one fundamental theorem of calculus, and that was it. Which, remember, it says if you want to evaluate a definite integral, you find an antiderivative for the integrand, and then plug in the bounds and subtract. So you'll notice now that we have, I can almost get rid of these blue parentheses, because now we're just looking at a normal single variable integral with respect to y. If we wanted to evaluate that, we would need to find antiderivatives of these two terms. So we'll get something like 64y squared minus y squared. We're evaluating that from 0 to 2, plugging in values of y. I mean, it's obvious now that we're plugging in y, but I do it just out of habit, writing this y equals 0 part. Cool. And when we do that, 2 squared is 4. 4 times 64 is 256, I think. And then we're subtracting 4. When we plug in 0, both of these terms are 0. So we would kind of implicitly be doing something that looks like this. Great. And then, we just need to subtract. We get 252. That is the answer. I think that's the answer. I mess up arithmetic all the time. I hope I didn't do that now. If I did, I will put a on-screen correction pointing out where I messed up. It's worth noting, going back to that example from the beginning where we added up the numbers in that grid in 2 different ways. We did it in 2 different ways, which has an analogy here, right? We integrated with respect to x first and then y, because that was just sort of the way I talked about it when I was doing the example. But if I carve out a little space here, and I'll say that we could evaluate, kind of thinking like we're adding up vertically first. We evaluate the integral with respect to y first, noting that we have to put the correct bounds for y. Y goes from 0 to 2. That would be the thing inside these parentheses to start. And then we would integrate with respect to x, where x goes from 1 to 4. So we could evaluate this and we would get the exact same number. We would get 252, because for the same reason as with that grid, right? It's just sort of a different way to think about adding up all of those numbers. So this flexibility, when it comes to evaluating double integrals, whether you want to do it with respect to x first and then with respect to y, or with respect to y first and then with respect to x, that can be useful sometimes. Sometimes it makes more sense to evaluate an integral in one order than the other based on the nature of the integrand. We'll see an example at some point where you have an integrand that's easier to integrate with respect to x first than with respect to y, or maybe the other way around. And so being able to set up the integral in either order will kind of give you the ability to choose the way that is easiest to compute. All right, so the last thing we have to do today is talk about what happens when the region of integration is not a rectangle. So here's an example problem I'll use to sort of motivate that. And just like before, I kind of always do this. I'm gonna write down like, what's the goal? Just to translate the problem, we wanna compute the double integral over the region. It's not given a name, so let's give it, and let's just call it t for triangle. The double integral over this triangle t of the function cosine x plus y. And we're given sort of a verbal description of what t is. But again, it'll be really helpful if we have a picture. So let's draw that. So there are my x and y axes. So we're told that the region is bound by the line y equals 2x, which let's say, yeah, that's good enough. This is y equals 2x, the line. And the line x equals 2 is a vertical line that looks like this. and the line y equals 0 is the x-axis. So we have these 3 lines, and we get a triangle. The triangle is this blue thing here. And also, I'll note again, just like before, this is the filled in triangle. I've only drawn the border because I want to draw some annotations on the inside, but really it's the whole like 2-dimensional triangle, not just the blue lines that I've drawn here. So to evaluate this, we're not going to go to Riemann sums this time, but we're going to think about like if we want to set up an iterated integral to compute this, right? We always compute double integrals by turning them into iterated integrals. We need to be careful when we're writing the iterated integral. We need to be careful about what the bounds on x and y are. And to do that, I want you to be thinking about that same thing from before. We're going to take this region, we're going to slice it into pieces, and then on each piece, we'll multiply the area of the piece times the value of this function on that piece, and then we'll add all those together. And it's in the adding of them together that we really want to be like focusing, because you can imagine like there was this grid here that we had gotten by like slicing this region into pieces. And even though it's not a like complete rectangular grid, it's still got like rows and columns. And you want to ask yourself, do you want to add up all of the rows first and then get a bunch of row sums that you would add up by a vertical sum, or the other way around where we add up all the columns first and then add up all of the column sums with a horizontal sum? So you get to pick, and really both ways will give you the same answer. For this one, I'm going to add vertically first. So I'm going to like draw in this little thing here. I'm going to add up the vertical columns first, and then I'll get a bunch of column sums that I'll add up horizontally. What that means in terms of the integral, which maybe we can just jump right into it, is that we're going to integrate with respect to y first because we're adding up vertically. And now the complexity is that since this isn't a rectangle, all of these columns have different heights, right? They all extend from y equals 0 up, right? They all start at the x-axis, but their upper bounds, it looks like their upper bounds depend on x. If we look at like an x value between 0 and 2, say here, then this column extends from y equals 0, which is the x-axis, up here to a y value that depends on x, right? This is the y coordinate here. If this is x, the y coordinate here is 2x, because this point lies on the line y equals 2x. What that means for our iterated integral is that the bounds on y are going to depend on x. So if I want to write that, I'll write an integral. This is going to be the integral with respect to y. Y is going to go from 0 to 2x. The integrand is cosine x plus y dy. So that's what's going to go inside our blue parentheses here. And I'll note that the bounds on y, so these integral bounds, depend on x. So that would be what I call the inner integral here, the one that we evaluate first. And you can think like, and it's like we're thinking about it like we're adding up all of these columns of numbers. Now, once we add up all the columns, we get a bunch of like column sums down here. And to add all those up, we're just integrating with respect to x. And here, the bounds on x will be constants, right? X is just going to go from 0 to 2. So we can put our dx here, and then our integral on the outside will be from 0 to 2. So this iterated integral here is how we would set up the integral over this region. I'll note, okay, there's a couple things to note. First, the integrand, cosine x plus y, I didn't talk about that at all. It has no bearing on how you're setting up the bounds. The bounds have everything to do with the region over which you're integrating, this region T, and nothing to do with the integrand. Another thing is, just like before, we could do this in the other order. And you might be wondering, like, before when we did the integral over the rectangle, we just swapped these two orders for these integrals in this dx dy, and we would have gotten, if we did the same thing here, we'd get something like the integral from 0 to 2x, and then the integral from 0 to 2 of cosine x plus y dx dy. I will caution you against doing this because there's sort of like a issue here. If you were to integrate, remember we integrate from the inside out, we'd integrate with respect to x first and then plug in these bounds. And then we'd integrate with respect to y and plug in these bounds, and the answer we would get would depend on x, which doesn't make sense because the answer should be a number. So I'll note by saying that you can do this integral in the other order by integrating with respect to x first and then y, but this isn't how. All right, so maybe I'll do something aggressive, like circle it in red and like put a big X through it. Don't do this. It doesn't even make mathematical sense, is what I was trying to say by saying like if you have bounds that mention X on the outside integral, then like this isn't even going to be a number when you go to evaluate it. So, but of course, if you do want to set this up in the other order, in the order where you're integrating with respect to x first horizontally and then with respect to y. You still can, but you need to do sort of a similar thing that we did to build this up, which is you might even like want to go like draw this picture again and draw in these like horizontal slices and think about, you're integrating with respect to x first. The lower bound on x is going to be whatever this x coordinate is, which will probably depend on y, and the upper bound on x is going to be 2. All right, I'm not going to do that one here. I'm going to leave it to you if you want to figure that out on your own. It's a really good exercise for this specific example. The last thing is like I didn't evaluate this. I promise that you evaluate it in the same way as we did with the rectangle one, where you integrate with respect to y, plug in these bounds. Even though it depends on x, it's okay because the next thing you'll do is integrate with respect to x. And then if you also want to practice further and set up the integral in the other order and evaluate that, you can check yourself and see that you got the same thing for both orders, right? They should always be the same. All right, so there we go. That's an introduction to how we set up double integrals. And there was a lot there, right? There's thinking about the region, like the geometry of the region and how that influenced the bounds, and talking about the order of integration also sometimes matters. There's that whole thing, thinking about like whether you want to integrate vertically first or horizontally first. This is something that takes everyone a while to get used to. I think it's one of those topics that it just feels like impenetrable at first and really difficult, but you're going to be practicing this a lot, right? We're going to be practicing setting up lots of different types of double integrals, and after a while, you'll become a lot more comfortable with it, and it'll become something that you just do as part of, some other computation down the line. All right, so good luck practicing. Thanks for watching, and I'll see you in the next video.